Next, we're going to continue discussing some financial formulas. Here, we're going to discuss savings. Savings formula. And to motivate this, I'm going to give an example, and we'll use this to derive a formula. Now, a complete derivation of this formula does require an observation, usually making Calc 2, and I'll make that observation. But I'm not going to ask you to prove this formula. This is just to see how what we're discussing with savings follows from our compound interest formula. So here, you deposit $100 per month, and we're going to assume that these deposits are on the last day of the relevant time period. So on the last day of the month, so you deposit $100 per month on the last day of the month into an account that earns 1.8% interest per year, and this is going to be compounded monthly. And the question will be, how much is in the account after 5 years? And to figure this out, so we have $100 per month. It's earning interest monthly, and it's compounding monthly, and it's asking about what happens after 5 years. So what we're going to do before using the formula, what we're going to do is think about what happens each month, and we're going to start at the most recent month. So the most recent month, the 60th time you make the deposit, is at the end of the 5 years. So at the end of 5 years, that's not going to earn anything beyond, well, it's not going to earn anything, so it's going to be worth that first $100. So what about the second to last month? Well, you deposit at the end of the month, it's $100. It's earning interest during that last month. So there's going to be one period during which this earns interest. So for this second to last month, we could ask, a sub question could be, you deposit $100 into an account, it earns annual interest 1.8%, compound monthly. How much is in the account after 1 month? Well, we would use our compound interest formula, which would give us 100 times 1 plus 0.018 divided by 12, the number of compounding periods, times, or not times, raised to the 12 times the time, which converted into years is 12 times 112. For this lecture and the next couple of lectures, I am going to use just the compound interest formula with R over M. You could do these with I. I'm going to do them just for annual interest rates, and then you can translate them over. Like with this one, I would be whatever 0.18 divided by 12 is, and the exponent would be 1 because it's 1 month. But this amount, 100 times 1 plus 0.018 over 12 raised to the 12 times 112 is the amount the second to last $100 earns at the end of 5 years, because it's being deposited at the end of month 59. So it earns interest for 1 month. What about the third to last deposit? Well, the last deposit is just worth 100. The second to last is worth 100 times 1 plus 0.018 over 12 to the 12 times the 12. So 1. What about the third to last? Well, you're still starting with $100, but this one's going to earn interest across 2 compounding periods. So $100 times 1 plus 0.018 divided by 12 raised to the 12 times 2 compounding periods. Or 12, times 2 compounding periods times 2 months, which in years is 2 12s. And this is going to keep going on I should have written plus dot dot dot. My second dot with what I wrote before wasn't a dot. It was a middle of a line dot. But this keeps going on. So what we have written is the last amount. What we have written is the amount that the last deposit is worth after 5 years, and then what the second to last deposit is worth after 5 years, and then what the third to last deposit is worth after 5 years. And now that keeps going on. And what is the first deposit worth? Well, it starts out as 100, but it earns interest. How much interest does it earn? I should have written that lower. Well, in your notes, if you're taking notes, you could write that lower. With the chalkboard, this would be easier. But across how many compounding periods is the first $100 you deposit accumulating interest? Well, 60 months. We're depositing at the end of 1 month. So this is going to earn interest during month 2, during month 3, all the way through during month 60. So there are going to be 59 compounding periods across which this earns interest. So this last exponent, 12, is the number of compounding periods per year, and it's earning interest across 59 months, which is 59 12th years, and that should be an exponent. So if we want to figure this out, we would just have to add all of these together. Now notice we did skip over 6 of them. So you would have 60 total computations to do. But there's a nice theorem that's covered generally in Calc 2. So I'll just say equals by a Calc 2 theorem. There's a nice way to add up a lot of these things. And those 60 terms equal this formula. That's a 60, that exponent. Equals all that, 100 times 1 plus 0.08 over 2 raised to the 60. So that's our, the large quantity in parentheses in each of those terms. And now it's raised to the 60 minus 1 all over the periodic rate. And so to add those 60 terms together, all we have to do using this theorem is compute this last quantity, and this equals approximately $6,237.37. And a derivation of the general savings formula follows very similarly to that example. I'm not going to have room on this page to write it, so I will write it on the next page. Okay. Let's call this theorem. Savings formula. A periodic deposit D per compounding period a periodic deposit D per compounding period. So right here, we have a deposit per compounding period, and we're depositing at the end of each compounding period. If we don't make that, I probably should have mentioned this while the other example is on the screen. If we don't make it at the end of the compounding period, we would have to adjust the formula by a 1. Like instead of 60, I guess it would be 61. So we're not going to worry about that. We'll just make the assumption that we're doing depositing at the end of the compounding period. A periodic deposit D per compounding period, earning interest at annual rate R compounded n times per year grows, that says grows, Grows, after T years. So this formula is going to be in terms of an annual rate. You could make the adjustment for the periodic rate. Grows after T years to A. We'll call it A equals D times, I should write it lower. I'm going to write it lower. Now I don't know where to scribble out because I moved my page. Okay, so let's scribble that out. And it grows to, maybe I should write it a little higher. Sorry, I moved my page and now I don't know where I am on this. Well, that's okay. To A equals D times 1 plus R over M to the MT minus 1 all over R over M, and we'll end that bracket. So D times 1 plus R over M to the MT minus 1 over R over M. That bracket isn't. Okay, I'll do it a little better. And this parallels the previous example. But let's go to another page and let's do another example. You deposit $5,000 on the last day of each year into an account earning 0.91% per year compounded annually. How much is in the account after 3 years? Well, we're just going to use our savings formula now because we don't have to derive it. This one wouldn't be that rough to, just do the 1 year, then the next year, then the next year, and add them together. But we'll use the savings formula. So A equals the periodic deposit, $5,000, times 1 plus our interest rate, 0.0091. Remember, convert that to a decimal. It has annual compounding, so our number of compounding periods per year is 1, raised to the 1 times our number of years, which is 3, and this is all over 0.0091. These dividing by ones, you technically don't have to write the dividing by ones, but I will for this example to follow. But in your homework, if it's a 1, you don't have to write it in the worksheet. And this is approximately equal to $15,136.90. And this answer does make sense. Small interest rate, $5,000 a year for 3 years, so it's only a little bit about $15,000. So that was the savings formula, which we used to figure out what how a periodic deposit accumulates. But we could flip that around. So in the savings formula, we used it, we figured out how a periodic deposit grew after a certain time period. We could flip that around where, say we want to figure out, say we want an amount after a certain time period, and we want to figure out what periodic deposit will give us that. Well, that would reduce to just solving the savings formula for D, the periodic deposit. And I'm going to call that a different formula called the payment formula. So let's just look at this example. You wish to accumulate $15,000 over 18 years using, that's a screw up right here, using an account which earns 5% per year, compounding monthly. And the question will be, so we want to accumulate $15,000. And the question will be, what monthly payment does this for us? Well, what monthly payment does this? Well, to do this, we'll solve the savings formula for the period, in this case, the monthly deposit, but in general, periodic deposit, for D, and we get the payment formula. So to solve that for D, the savings formula is a large fraction times D. So what we can do is multiply both sides by the denominator of the fraction and divide both sides by the numerator. Or just multiply by, flip the fraction around and multiply both sides. So the payment formula, the variables are the same setup as the savings formula because they're, well, it's the same formula, just rearranged. So I'll just write the formula here. Payment formula, D equals A times, in the numerator, R over M, and in the denominator, 1 plus R over M, MT minus 1. So notice, if you flip that numerator around and switch A and D, you do have the payment or the savings formula. So what would that be in this case? Well, D equals 5,000. So D equals 15,000, the amount that we want to have at the end of the period, times 0.05 over 12, all over 1 plus, sorry, I overlapped the parentheses. 1 plus 0.05 over 12 to the 12. We are going across 18 years in the example, so the time is 18. It's compounding monthly, so our compounding, the number of compounding periods per year is 12. So we have 12 times 18 there, and this is approximately equal to 42.96. So deposit 42.96 per at the end of each month, and that'll give you, with this rate, 15,000 at the end of that year. So right there, we really had only one formula, but we looked at 2 applications of it. Let's look at another. I'm actually going to make this next one a separate video.